All right, so we are starting class. I'd like you to put the phones away. I think you know that that is rude to have that out, and it's becoming more and more of a problem. I spent about 4 hours getting class ready today, so I'd appreciate you being engaged. Thank you. Um, what I want to do first is if you have your organic molecule and monomer paper, pull that out. And we were looking at how organic molecules get represented when they are drawn. And so I've put out in front of you some pieces for molecules. And most of you should have a molecule that looks like this, right? That should be at your desk. All right, so what does the black atom represent? Carbon, right? So most of organic molecules is going to be made of carbon and hydrogen. There tend to be more hydrogens, but they're lighter weight, so the mass is almost entirely carbon. What do the reds represent? Oxygen. Okay, so this has two oxygens and one carbon. So that being the case, what would we call this molecule? CO2. What would we call that? Carbon dioxide. Okay, so you're going to need the pieces of this to do some of the other things. So on this paper, it talks about how we have the molecular formula, which just lists the number of atoms, so like CO2. And then we sometimes draw out the structure, but a lot of organic molecules are really big. And so instead of drawing out the whole molecule, we do what's called a line structure. So, first, what I'd like you to do is make a 3-carbon chain. And some of you already have some kind of a chain, but put together a 3-carbon chain. All right, so it probably looks something like this, right? Okay. So if you were to draw the line structure of that, it would follow the shape of that bond. So it would look like this. We'd have carbon here, a carbon here, and a carbon here, right? Okay, each of these spokes that are coming off have to be attached to something. If we don't draw them on a line structure, what are we supposed to assume is attached there? Hydrogen. Whoops. So if you count the number of spokes sticking off on your little model, how many hydrogens are there? 8, right? So 3 on each end and 2 in the middle. Now we could figure that out from the line structure by saying this carbon only has 1 bond, so there must be 3 because each carbon has 4 bonds, right? This one has to have 3, and this one has to have 2. Okay. If you were to make a water molecule using this kit, it would look something like this. So it would have red and 2 hydrogens. But I haven't put any hydrogens on your table because we don't tend to draw the hydrogens. We do usually draw the hydrogens in the case of an alcohol, but for today, just to keep things simple, we're going to assume that any spoke coming out of an oxygen that doesn't have something is also a hydrogen. So how could you turn this into an alcohol? What is the group of an alcohol if you look in your notes? Max, can you put your phone down? Thank you. It's going to be a carbon attached to what? Oxygen and hydrogen. All right, so in your case, we're going to leave the hydrogen off. So you're going to take one of the gray pieces and attach it on your molecule. And then you're going to attach one of the red ones. That's going to make an alcohol group. All right, so let me see yours. Okay, so you don't have it on your 3-carbon chain. That's okay. You still have an alcohol. All right, so yours is methanol. All right, you need to make sure that your alcohol only has at most 2 carbons because you only have 4 carbons. And so you're gonna need the 2 other carbons for something else. All right, so if it's got 1 carbon, that's fine. If it got 2 carbons, that's fine, but no more than 2 carbons. Okay, then you are going to put your 2 other carbons together. And apparently I only have here. So this is a molecule we don't normally do as a line structure because as a line structure, it would just look like that. That'd be a little weird. We're going to turn this one into a carboxylic acid, and that's a little bit trickier. So this carbon is going to have an alcohol. So go ahead and put an oxygen on one end to make it an alcohol. And then it's going to have a double bonded oxygen. And the short little gray pieces aren't long enough for that. So you're going to take apart your carbon dioxide molecule and build it like this. So it already has longer pieces that are curved and they'll be shaped in the right way. Okay, so to the same carbon, you're going to attach 2 different oxygens. One's going to have a single bond, one's going to have a double bond. All right, so it should look something like this. Okay, so this is a carboxylic acid, and for some reason my oxygens have extra spokes. You shouldn't have extra spokes on yours. So it should look like this. This is a carboxylic acid. So when we make condensation polymers, I'm gonna shift this over. When we make condensation polymers, we take an alcohol and we take a carboxylic acid and put them together. So you should have one molecule that somewhere has an OH. So it might be just 1 carbon, it might be 2 carbons. There should be a carbon over here. And what we're going to do is, in order to condense this, we're going to pull out a molecule. So from your 2 pieces, you're going to pull out a water molecule among these 4 and then connect to the oxygen on both sides to a carbon. So let's see if you can do that. Okay, so you should have something that kind of looks like this up there. So we've got this carbon here has a double bonded oxygen and it has an oxygen that has a single bond. So this is called an ester, and the process of making that ester is called condensation. So we're going to join these 2 together and make C double bond O, O, C, C, and this part here is called an ester. And so a lot of the molecules that are in scents that we enjoy, especially flowers and fruits, have esters in them. One of the ones that has the most identifiable smells is isoamyl alcohol. So you can hear, isoamyl acetate. So the 8 is the ending for the ester, and that smells like bananas. So if you've ever had banana flavored anything, it's got an ester in it that is found naturally in bananas that smells like bananas. Okay, so we are going to take a minute to talk about the 6 different types of plastic that have the symbols numbered 1 through 6 that you can theoretically recycle. And then we're going to do some hands-on stuff. So let me get this pulled up here. Okay, so we will look for just a second at comparing the 2 ways of making a polymer. So this is something that may appear on your quiz next week. Definitely may appear on your final exam. So we've talked about addition polymers, and that was our polyester, not our polyesters, our polyethylene, and polypropylene is also made this way. So we use a free radical. And what is a free radical? A free radical has an unpaired electron. So remember, electrons like to travel in pairs. There's 2 electrons in a bond or 2 electrons in a lone pair. So if there's only one, it's kind of hungry for a partner. and it's going to go around and attack anything that it thinks will give it an extra electron. And double bonds have lots of electrons, so it's going to go there first. And so we might call a carbon compound with a double bond an olefin, or we might call it an alkene. And so those are our monomers. Remember, the monomers are the single pieces that make up the larger thing. So in the case of addition polymers, we usually have the same monomer over and over again. Lots and lots of ethene with these double bonds. And all of the atoms become a part of that polymer. So it's called addition because you just add them all together. There's no subtraction out of it. Okay. In condensation, we have two different functional groups. So instead of having this free radical coming in from the outside, our monomers have the two different functional groups. So we looked at the alcohol and the carboxylic acid. When they join together, a water molecule leaves. So the ones that we'll care about, the water molecule is the small molecule lead. And so that is forming an ester, and we've all heard of polyester, right? So polyester is made by this joining of these molecules. So if I just have those two and I don't have anything else on the other ends, then it kind of stops there and I just get a big molecule. I don't get a long chain. So a lot of times what will happen is we will use a molecule that maybe has an alcohol on one side and an acid on the other, so it can form a chain. Or we might do a mixed polymer, in which case we have some monomers that have two carboxylic acids and some monomers that have two alcohols. And so they can join together at each end. In this case, in the case of a condensation polymer, not all the atoms from the original monomers are part of the molecule, the polymer, because the water is leaving. So you have water left behind. Okay, so condensation, this is what we looked at, the carboxylic acid and the alcohol. The red circle is showing that water molecule that's going to be pulled away and an ester form. So that's where we get polyester. All right. So you might have two different monomers, or you might have one monomer that has two different functional groups on it, like I just said. Polyethylene terephthalate is recycling number 1. And so I know on your chart in there, one of the tables in there, it asks you to list the big 6. So number 1 is PETE, or sometimes it's just PET. And so you need to be able to pair the number with the abbreviation. I'm not going to expect you to remember the whole polyethylene terephthalate. But this is a polyester, and it is formed when this molecule, the terephthalic acid, so that's the carboxylic acid there, combines with ethylene glycol. So glycol has an OH group. The ethylene glycol is the same thing as antifreeze, and it has kind of a sweet smell to it. So it's important that if you have antifreeze that you keep in your garage, that you make sure it's not leaking and you keep it away from pets, because pets will just lap it up like something delicious. Dogs more than cats. Cats don't like sweet things. But it's poisonous. Same thing with little kids. So, you know, if you've got nephews, nieces, anybody running around, a little brother or sister that might get into something if it smells sweet, keep ethylene glycol away from it. All right, so that's the formation of recycling number 1. Now, recycling number 1 was made in response to the soda industry. So we had the addition polymers, the polyethylenes, and you could put water in them. But Coke and Pepsi and those things were long stored in glass bottles. And what they would do, and you can still do this with things like Ale8, you can take the glass bottle to a recycling center or back to the company, and they clean and sterilize it and reuse the bottle over and over again. And that's what they used to do with Coke bottles. And I have a vague memory from when I was really little of them doing this. But at that point, they had developed this chemical. When they tried to use the polyethylene, that one, when you have that pressurized carbon dioxide in there, it would break the bottles. And so it wasn't strong enough to contain the pressurized carbon dioxide. So this is a stronger material that can contain the carbonation. So if you have I know people don't buy sodas as much as they used to, but if you do, and you get it in a plastic container, you'll notice that it has a recycling number 1, whereas like your milk bottle or your water bottle is going to be recycling number 2. So the polyethylene is cheaper to make and it's easier to recycle, but this is stronger, so it works for our sodas. All right, so once that molecule forms, then on the other sides of the molecule, since ethylene glycol had an alcohol here and an alcohol here, this can join up with the next terephthalic acid, and this can join up with the next ethylene glycol. So it's what's called a heteropolymer, hetero meaning different, because it can alternate between these two things, forming a long chain of the alternate esters. All right, so peat, recycling number 1, is very strong and it's good for high pressure things. They pull the fibers, they can pull it into fibers like for clothing. So you can make clothing out of it, or into sheets. Mylar balloons tend to be made out of peat and then coated with something to make them look more metallic. Oops, sorry, I didn't advance for you. All right, we good on this slide? All right, I'm not going to do formation of protein right now because I don't want to be skipping around. So we will talk about that on Tuesday. Remember that we do have the quiz that will cover up through the big 6, which I'm going to finish the others on the board here. You also have a chart in your book that you can look at that has that information. And then and the formation of the different types of polymers. Where's my stop share? Can I click on that? There we go. Okay. So let's take a look at some of the other polymers. Let me move this out of the way. So one was PET. Sometimes we have PETE, depending on who's writing the label. And this is the number that you'll see in that recycling triangle. Okay, this one can be recycled in bottle form most places. What we find around here is that if you have anything else made out of the recyclable plastics beside a bottle, they don't want to recycle it. So if you have like a cookie container that has a number 1 on it, they don't want to recycle that. I don't know why, but the bottles, I guess, are easiest and cheapest to recycle. So feel free to do bottles, but if you have like your cookie containers, not much you can do. Okay, so this can withstand high pressure. And we can use it for soda or for Mylar balloons. Oddly enough, number 2 was one of our first polymers that we made. So this is HDPE. So the PE here stands for polyethylene. So remember, ethylene was that double bonded thing that we did the addition polymer for. HD stands for high density. And so one thing I might ask you to explain on your final exam or on your quiz is, why is it high density compared to low density polyethylene? So I'm going to go ahead and put low density on as number 4. So what is the difference between those? What makes one high density and the other not? Remember? So if we think of all of these polymers as like long strands, this one is just like a basic simple strand. But if you've ever tried to pick up the branches that have fallen down in a yard and put them into a pile, when there's lots of things sticking out of them, they don't stack together nicely, right? And so you might have to break off the side branches to get them to pack together. So this one is branched chains. And this is single chain. Okay, so the polymers might be lined up like this, whereas this one, we can't get things close together because the polymers are all sticking out. Okay. Number 3 is PVC, polyvinyl chloride. So we're not going to talk about the vinyl group, but it's just some more carbons. And this one most famously is used for those white pipes that they have for plumbing. So it replaced lead pipes and things like that. It's used in a few other places, but the chlorine isn't really great for our health, and we don't like to burn the chlorine because that puts chlorine in the atmosphere. So we try to stick with things that are going to be like long term, it's going to stay in its place and it's not going to get burnt. So this might be used for pipes. 5 is polypropylene. Which is just like polyethylene, but ethyl means 2 carbons and propyl means 3 carbons. So we start with a molecule that has a double bond and a single bond. And so we have little things sticking off of it. And so this one is often used for like mayonnaise or margarine or things like that because it's resistant to the oils and the fats that might start to dissolve the polyethylene. And so that's why we use that. So these are often in food containers. And then 6 is PS, which is polystyrene. Again, styrene is another functional group we're not going to talk about. And this is also used for some of the same things that polyethylene is, not for the high pressure things, but it's used for like clamshell things, for like you go to the bakery and you get cookies or something like that in a clear container. It's sometimes used for that. It's also used for plastic cups. And for foam. And there is a company that makes foam to insulate houses that calls this styrofoam. So styrofoam is actually the brand name. Just like Kleenex doesn't mean all tissues, it's a brand of tissues. Styrofoam is actually just that particular kind of foam. But usually when we say styrofoam, we're referring to polystyrene. This one, we're going to discover in a little bit, is not resistant to certain chemicals. I'm not going to write it down right now because I want you to be able to kind of discover that as you do some of the activities. Okay, so that's our big 6. Were there other things on the chart that I didn't give you? Okay,